Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Matrix Eigenvalue Problem under the paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. Idea of eigenvalue of a matrix is introduced and its importance is discussed. A complex vector space is introduced as a prelude to eigenvalue problem. The characteristic equation of a matrix and its relation to eigenvalues and eigenvectors is obtained. Symmetric, antisymmetric, and orthogonal matrices are defined. Orthogonal transformations are introduced and their properties are discussed. Similar matrices are defined and its importance in diagonalization of a matrix is discussed. Unitary, Hermitian, and Antihermitian matrices are defined and properties of their eigenvalues are proved. In this unit, we will be dealing exclusively with square matrices. Let A be a square matrix of order n and X is a column vector of order n. Then the operation of A on X will yield some other column vector Y. That is, AX will give Y. We can look upon the matrix as a transformation in the vector space of column vectors. The operation of A on X transforms it into, in general, a different vector Y. However, there exist certain special non-zero vectors which have the property that the matrix A operating on them yields simply a multiple of the same vector. If X is one such special vector, then AX is equal to lambda times X. The problem is to be viewed as given a matrix A, we have to find the unknowns X and lambda. One solution to this problem is X is equal to 0. This is the trivial solution and is of no interest to us. The problem of systematically finding such special non-zero vectors for a given square matrix and the corresponding scalars A is referred to as the eigenvalue problem. Let us begin with the inner product. Let U and V be vectors in C raised to power n. Then the Euclidean inner product of U and V is a scalar which is defined as U dot V is equal to U1 bar V1 plus U2 bar V2 plus so on till UN bar Vn, where the bar stands for the complex conjugate. Given vectors U, V and W, U dot V is equal to V dot U bar. Also, U dot within the brackets V plus W is equal to U dot V plus U dot W. Then the inner product of K times vector U dot vector V is equal to K bar times the inner product of vector U and V. Inner product of vector U with K times vector V is equal to K times the inner product of vector U and V. The inner product of vector U with itself is greater than equal to 0. U dot U is equal to 0 if and only if U is equal to 0. The Euclidean norm or length of U in C raised to power n is defined as norm of U with itself is equal to square root of U dot U. The Euclidean distance between the vectors U and V is defined as D times UV. D of UV is defined as G of UV, which is equal to the norm of vector U minus V with itself. That is, norm of vector U is equal to square root of modulus of U1 square plus modulus of U2 square plus so on till modulus of UN square. Then DUV is equal to square root of modulus of U1 minus V1 whole square plus modulus of U2 minus V2 whole square plus so on till modulus of UN minus Vn whole square. Two vectors U and V whose inner product is 0 are said to be orthogonal. If further, both the vectors have been normalized, they are said to be orthonormal. In an n-dimensional vector space, we can always choose n vectors which have unit norm and are mutually orthogonal. That is, we can always choose an orthonormal basis. Let us take up the examples. Let vector u is equal to 1 and iota, vector v is equal to 1 plus 2i and 1. Then the inner product of u and v is equal to the row vector 1 minus iota into the column vector 1 plus 2 iota and 1, which equals 1 plus iota. Similarly, the inner product of v and u can be calculated as the row vector being 1 minus 2 iota and vector 1, the column vector into the column vector 1 and iota, which equals 1 minus iota. That is, it is equal to the inner product of u dot v bar. So, v dot u is equal to u dot v bar. Now, u dot u will be equal to the product of row vector, which is 1 and minus iota, with the column vector 1 iota, which equals 2. This implies that the norm of vector u with itself is equal to square root of 2, which implies u prime is equal to vector u divided by square root of 2 is normalized. Let w is a column vector given as 1 minus iota. This implies that the inner product of u with w will be equal to the row vector 1 minus iota multiplied by the column vector 1 and minus iota, which equals 0. This implies that u and w are orthogonal. W prime, which is equal to w by square root of 2, is normalized, which implies that u prime and w prime are orthonormal. We next discuss about the characteristic equation. Our objective is to find the eigenvalues and eigenvectors of a given matrix A, which is specified by Aij. By taking the lambda x term to the left hand side in equation 1, it can be rewritten in the form A minus lambda times identity matrix into matrix X is equal to 0, which implies the equations of the form A11 minus lambda into x1 plus A12 x2 plus so on till A1n xn is equal to 0. A11 x1 plus A12 minus lambda into x2 plus so on till A1n xn is equal to 0. The last equation being in the similar way an1 x1 plus an2 x2 plus so on till ann minus lambda times xn is equal to 0. By Cramer's rule of the last unit, this homogeneous system of equations in Xi has a non-trivial solution if and only if the determinant of the coefficient matrix is identically 0. Determinant of lambda is equal to d of lambda is equal to determinant of the matrix A minus lambda I, which equals determinant of the matrix with the first row elements being A11 minus lambda, A12 and so on till A1n, second row being A21, A22 minus lambda and so on till A2n, and the last row being AN1, AN2 till ANn minus lambda, which equals 0. The matrix A minus lambda I is called the characteristic matrix of A. The determinant D of lambda is called the characteristic determinant of A. When the determinant D of lambda is written in expanded form, it will be a sum of n factorial terms. Each term will consist of exactly n factors. Only one of the term will consist of the factors A11 minus lambda, A22 minus lambda, ANn minus lambda. The determinant is a polynomial of degree n in lambda. Equation 3, which is called the characteristic equation, and the polynomial is called the characteristic polynomial of A. Eigenvalues of a matrix A are the roots of the characteristic equation of A. According to the fundamental theorem of algebra, a polynomial of degree n has exactly n roots, including complex roots and multiple roots. Hence, a square matrix A of order n has exactly n eigenvalues. Once the eigenvalues are evaluated, the eigenvectors are obtained by solving the system of n linear homogeneous equations described in equation 2. An eigenvector is determined only up to an overall constant. The constant is usually chosen so that the vector x is normalized. The order m lambda of an eigenvalue as a root of the characteristic polynomial is called the algebraic multiplicity of lambda. The number m lambda of linearly independent eigenvectors corresponding to lambda is called the geometric multiplicity of lambda. Thus, m lambda is the dimension of eigenspace corresponding to this lambda. It is clear that m lambda is less than or equal to capital M lambda. Let us take up some examples now. Consider matrix A is equal to 2 cross 2 matrix with the first row being 1, 0 and second row being 2, 3. The characteristic equation is determinant of the matrix with the first row being 1 minus lambda 0, the second row being 2, 3 minus lambda is equal to 1 minus lambda into 3 minus lambda, which equals 0. This implies that the eigenvalues lambda will be equal to 1 and 3. So the eigenvector for lambda is equal to 1 can be found out to be by using the equations 0 times x1 plus 0 times x2 is equal to 0. 2 times x1 plus 2 times x2 is equal to 0, which implies x2 is equal to minus x1. So the normalized eigenvector is given by 1 by square root of 2 into the column vector 1 minus 1. Now the eigenvector for lambda is equal to 3 can be found out using the equations minus 2 times x1 plus 0 times x2 is equal to 0, 2 times x1 plus 0 times x2 is equal to 0, which implies that x1 is equal to 0 and x2 is equal to arbitrary. So the normalized eigenvectors will be the column vectors with the elements 0 and minus 1. In another example, consider matrix A to be 2 cross 2 matrix with the first row elements being 0 and minus 1, the second row being minus 1 and 0. Characteristic equation will be determinant of the first row of the matrix with the first row being minus lambda 1, second row being minus 1 minus lambda is equal to lambda square plus 1, which equals 0. This implies eigenvalues lambda will be equal to minus iota and plus iota. The eigenvector for lambda is equal to minus iota can be obtained using the equations iota times x1 plus x2 is equal to 0, minus x1 plus iota times x2 is equal to 0, which implies x2 is equal to minus iota times x1. So the normalized eigenvector is 1 by square root of 2 into the column matrix, which has elements 1 and minus iota. The eigenvector for lambda is equal to plus iota will be equal to minus iota times x1 plus x2 is equal. Eigenvector for lambda is equal to plus iota can be obtained using the equations minus iota times x1 plus x2 is equal to 0, minus x1 minus iota x2 is equal to 0, which implies that x2 is equal to iota times x1. So the normalized eigenvector is 1 by square root of 2 into the column matrix 1 with the elements 1 and iota. In this example, the matrix is real, but the eigenvalues and eigenvectors are complex. We next discuss about the symmetric, antisymmetric, and orthogonal matrices. We consider three classes of real square matrices that occur quite frequently in applications. A real square matrix A is called symmetric if A transpose is equal to A, and antisymmetric if A transpose is equal to minus of A. Real square matrix is orthogonal if and only if A transpose is equal to A inverse. Equivalently, an orthogonal matrix can be defined by the requirement A into A transpose is equal to A transpose into A, which equals the identity matrix. Considering an example, consider the matrices A of the form 3 cross 3 matrices, with the first row being 1, 2, 1, second row being 2, 3, minus 1, and the third row being 1, minus 1, and 2. We can see the matrix is a symmetric matrix as the transpose of this matrix is equal to the matrix itself. In another example, consider the matrix of the form with first row being 1, 2, 1, second row being minus 2, 3, and minus 1, the third row being minus 1, 1, and 2. We can see the matrix, if we take the transpose of the matrix, it is equal to minus of matrix A. So, the matrix is an antisymmetric matrix. Another example, consider the matrix A to be equal to first row being 0, 0, 1, second row being 0, 1, 0, and the third row being minus 1, 0, and 0. If we observe the A transpose, this is equal to the inverse of matrix A itself. So the matrix is an example of an orthogonal matrix. We next state a theorem which says that first, the eigenvalues of a symmetric matrix are always real. Secondly, the eigenvalues of a skew-symmetric matrix are pure imaginary or zero. The converse of the first part of theorem is not true. That is, symmetry is a sufficient but not a necessary condition. The second part, the matrix, a 2 cross 2 matrix of the first row being A0 and the second row being BC, where A, B, C are real, is not symmetric, but it has real eigenvalues A and C. We next consider the orthogonal transformations. A matrix A can be viewed as effecting a transformation in the space Rn, which transforms a vector x into a vector y. That is, y is equal to A times x. Transformation by an orthogonal matrix is called an orthogonal transformation. It can be shown that every rotation in a plane or 3-dimensional space or n-dimensional space for that matter is an orthogonal transformation. For example, a rotation by an angle theta in a plane is given by the orthogonal matrix A, which is equal to a 2 cross 2 matrix with the first row being cos theta sin theta, second row being minus sin theta and cos theta. We next discuss the properties of orthogonal matrices. First one is, an orthogonal transformation preserves the inner product and hence the norm in R raised to power n. That is, inner product of vector A with vector B is equal to the transpose of matrix A into B, which is equal to the row matrix with the elements A1, A2 and so on till An multiplied by the column matrix B1, B2 and so on till Bn is equal to A1, B1 plus A2, B2 plus so on till An, Bn. We will now prove it. Let capital A be an orthogonal matrix and let small a and small b be two given vectors. Let vector x is equal to A times matrix A and vector y is equal to B times matrix B, A. Then inner product of x dot y is equal to x transpose into y, which equals A times matrix A transpose into B times matrix A, which equals A transpose into matrix A transpose into matrix A into B, which equals A transpose into identity matrix into B, which equals A transpose into B and is in turn equal to A inner product of A and B. Hence, the theorem is proved. Second property is, a real square matrix is orthogonal if and only if the column vectors C1, C2 and so on till Cn and also its row vectors form an orthonormal system. Let us prove it. If A is orthogonal, then by definition, A transpose into A is equal to identity. A transpose into A is equal to the transpose of row vector C1, C2 and so on till Cn into row matrix C1, C2 till Cn. This equals the column matrix with the elements C1 transpose, C2 transpose till Cn transpose into the row matrix with elements C1, C2 till Cn. This can be written as a n cross n matrix with the first row elements being C1 transpose C1, C1 transpose C2 till C1 transpose Cn, the second row elements being C2 transpose C1, C2 transpose C2 till and so on till C2 transpose Cn, and the last row elements being Cn transpose C1, Cn transpose C1, Cn transpose C2 and so on till Cn transpose Cn. This can be written to be equal to the matrix of n cross n size with the first row being 1, 0 and all elements being 0. The second row being 0, 1 and rest all other elements being 0 till the last row being 0, 0, 0 till the last element being 1. On comparing the various terms of the two matrices, we obtain Ci.Cj is equal to Ci transpose into Cj, which equals delta Ij. If A is orthogonal, then the transpose of matrix A is also orthogonal. But the columns of transpose of matrix A are the rows of matrix A. Hence, the result is true for the row as well. Hence, the property is proved. The third property of the orthogonal matrix states that the determinant of an orthogonal matrix has the value +1 or -1. Let us prove it. Determinant of product of matrix AB is equal to determinant of matrix A into determinant of matrix B, and determinant of matrix A is equal to determinant of transpose of matrix A. From these two properties, the result follows, that is 1 is equal to determinant of identity matrix, which equals determinant of A into A inverse, which equals determinant of A into A transpose, and is equal to determinant of A into determinant of A transpose, or determinant of A into determinant of A, which can be represented as square of determinant A. This implies that determinant A is equal to ±1. Hence, the property is proved. We next take up the eigenbases. Eigenvectors of an n cross n matrix A may or may not form a basis for r raised to power n or c raised to power n. In considering transformations such as y is equal to ax, an eigenbasis is of great advantage because then we can represent any vector x uniquely as a linear combination of the eigenvectors. That is, x is equal to c1 times the vector x1 plus c2 times vector x2 plus so on till cn times the vector xn. If lambda1, lambda2 and so on till lambda n are the eigenvalues of matrix A, then the matrix A times vector xi is equal to lambda I times matrix xi. This implies y is equal to matrix A into matrix x, which equals matrix A into C1 times matrix x1 plus C2 times vector x2 plus so on till Cn times the eigenvector xn. That is C1 times lambda 1 into eigenvector x1 plus C2 times lambda 2 into eigenvector x2 plus so on to Cn times into lambda n the eigenvector xn. Thus, in terms of the eigenbasis, the effect of the matrix A on an arbitrary vector is to multiply the coefficient of each eigenvector by a scalar. Let us take up a theorem. The following theorem provides a criteria for existence of eigenbasis. If all the n eigenvalues of an n cross n matrix A are distinct, then the eigenvectors form a basis in R raised to power n. Let us prove it. Let R is less than n of the eigenvectors x1, x2, so on till xr be linearly independent. Then the set x1, x2 and so on till xr and xr plus 1 is linearly dependent, and so there exist coefficients C1, C2 and so on till Cr plus 1, not all 0, such that C1 times x1 plus C2 times eigenvector x2 plus so on till Cr plus 1 into eigenvector xr plus 1 is equal to 0. This implies matrix A into C1 times eigenvector x1 plus C2 times eigenvector x2 plus so on till Cr plus 1 into eigenvector xr plus 1 is equal to C1 times eigenvalue lambda 1 into vector x1 plus C2 lambda 2 x2 plus so on till Cr plus 1 lambda r plus 1 into xr plus 1. This equals 0. So this implies C1 into within the brackets lambda 1 minus lambda r plus 1 into x1 plus C2 into within the brackets lambda 2 minus lambda r plus 1 into x2 plus so on till Cr into within the brackets lambda r minus lambda r plus 1 into xr is equal to 0. This implies that C1 into lambda 1 minus lambda r plus 1 is equal to C2 into lambda 2 minus lambda r plus 1 and so on is equal to Cr into lambda r minus lambda r plus 1 equals 0, which implies C1 is equal to C2 is equal to so on till Cr equals 0. Since all eigenvalues are distinct, but now equation 5 reduces to Cr plus 1 into xr plus 1 equals 0, which implies Cr plus 1 equals 0. But we started with the assumption that not all scalar in equation 4 are 0. Hence, there is a contradiction and the result is proved. Consider a case that all eigenvalues are not distinct and yet the eigenvectors form a basis. For the matrix A, which is a 3 cross 3 matrix with the elements minus 1, 1 and minus 3 by 2, second row being 1, 1 by 2 and minus 3, third row being minus 1 by 2, minus 1 and 0, the eigenvalues lambda being minus 3 by 2 and 5 by 2, the eigenvectors are of the form 1 divided by square root of 6, 2 divided by square root of 6, minus 1 divided by square root of 6. The second one is 2 divided by square root of 5, minus 1 divided by square root of 5 and 0. The third one being 3 divided by square root of 10, 0 and 1 divided by square root of 10 are linearly independent. A symmetric matrix has an orthonormal basis. That is, eigenvectors of a symmetric matrix are not linearly independent but are mutually orthogonal. The similar matrices. Similar matrices play an important role in the diagonalization of a matrix. A matrix A hat is said to be similar to a matrix A if there exists a non-singular matrix P such that A hat is equal to P inverse into matrix A into P. This transformation from A to A hat is called a similarity transformation. Every non-singular matrix P will effect a similarity transformation. Let us consider a theorem which states, first, similar matrices have the same eigenvalues. Second, if X is an eigenvector of matrix A, then P inverse into X is an eigenvector of matrix A hat for same eigenvalue. Let us prove it. From A times X is equal to lambda into X, we have P inverse into AX is equal to lambda into P inverse X. P inverse into AX is equal to P inverse into A times identity matrix into X, which equals P inverse into matrix A into PP inverse X. This equals P inverse into AP into P inverse of X. This can be written as P inverse of X or lambda times P inverse of X. Hence, lambda is also an eigenvalue of A hat and corresponding eigenvector is P inverse of X. Hence, the theorem is proved. If we can find that the similarity transformation for which matrix A hat is diagonal, we say the given matrix has been diagonalized. This can be understood with the help of an example. Consider matrix A to be a 2 cross 2 matrix with the first row being 3, 4 and second row being 4 and minus 3. The matrix P is another 2 cross 2 matrix with the first row being minus 4 and 2 and second row being 3 and minus 1. Then P inverse is equal to 1 by 2 into matrix A with the first row elements being 1 and 2 and second row being 3 and 4. A hat will be equal to P inverse times AP, which equals the 2 cross 2 matrix with the first row elements being minus 25 and 12, second row elements being minus 50 and 25. So the eigenvalues of matrix A can be found out by the characteristic equation, which is 3 minus lambda into minus 3 minus lambda minus 16 is equal to 0. This gives lambda to be equal to minus 5 and 5. The eigenvalues of matrix A hat can be found using the characteristic equation minus 25 minus lambda into 25 minus lambda plus 600 is equal to 0, which again implies lambda to be equal to minus 5 and 5. Let us next consider the diagonalization of a matrix. Given a matrix A, if there exists a matrix similar to A which is diagonal in form, we say the matrix A has been diagonalized. It may not be always possible to diagonalize a given matrix. Let us take up a theorem. The first part of the theorem states, if the eigenvectors of an n cross n matrix A form a basis, then D is equal to x inverse into A into x is diagonal with the eigenvalues of A as the entries on the main diagonal. Here X is the matrix whose columns are these eigenvectors. Second part of the theorem says that D raised to power k is equal to x inverse into A raised to power k into x, where k take up the values 2, 3 and so on. Let us prove it. Let eigenvectors of matrix A be denoted by xi and eigenvalues by lambda I. So, matrix A into vector xi is equal to lambda I into matrix xi. Since xi form a basis, then the matrix X is equal to a row matrix with the elements being x1, x2 and so on till xn. This equals n cross n matrix. This equals n cross n matrix with the first row elements being x11, x12 and so on till x1n. Second row elements being x21, x22 and so on till x2n. And the last row elements being xn1, xn2 and so on till xn. The matrix X has rank n and is therefore non-singular. Now, A times X is equal to A into the row matrix with the elements x1, x2 and so on till xn is equal to the matrix with elements A times x1, A times x2 and so on till axn. This equals the matrix with the elements lambda 1 x1, lambda 2 x2 and so on till lambda n x1. So this can be expressed as the product of two n cross n matrices, where the first matrix has the first row elements being x11, x12 and so on till x1n, second row elements being x21, x22 and so on till x2n, and last row elements being xn1, xn2 and so on till xn. The second matrix elements, where the first row elements are lambda 1, the second matrix has the eigenvalues lambda 1, lambda 2 and so on till lambda n as the diagonal elements, and the rest all other elements being 0. This is equal to matrix X into matrix G. D is the diagonal matrix whose diagonal elements are the eigenvalues. On multiplying by X inverse from the left, we have X inverse into AX is equal to X inverse into XG, which equals matrix G. Now D raised to power k is equal to matrix G into D till k times. This equals X inverse into A times X into X inverse into A times X, which is repeated k times. This equals X inverse into A into A into A k times into x, which equals x inverse into a raised to power k into x. Hence, the theorem is proved. We next take up the unitary, Hermitian and Antihermitian matrices. We will deal with matrices that are complex now. The complex conjugate of the matrix A is the matrix A bar, in which all the elements are replaced by the complex conjugates. The Hermitian conjugate or transpose conjugate of a square matrix A, denoted by A star, is the matrix which is transposed as well as conjugate of A. So A star is equal to A bar transpose. In physics, and in particular in quantum mechanics, the word Hermitian conjugate is much preferred and the symbol used is A dagger. We will, however, continue with A star. Let us discuss some properties of Hermitian conjugate. The first property is the star of matrix A star is equal to matrix A itself. Then the Hermitian conjugate of matrix K times matrix A is equal to K bar into the Hermitian conjugate of matrix A. The Hermitian conjugate of the sum of matrices A plus B is equal to the Hermitian conjugate of matrix A plus Hermitian conjugate of matrix B. Hermitian conjugate of the product of matrices AB is equal to the Hermitian conjugate of matrix B into the Hermitian conjugate of matrix A. A matrix is said to be Hermitian if it is equal to its Hermitian conjugate. That is, A equals A star or Aij equals Agi conjugate. Anti-Hermitian or skew Hermitian if A is equal to minus A star or Aij equals minus Agi bar. Unitary if its inverse equals its Hermitian conjugate. That is, A inverse equals A star. The matrix is normal if A star equals A star A. From its definition, it follows that the diagonal elements of a Hermitian matrix must be real and that of an anti-Hermitian matrix must be pure imaginary. A real Hermitian matrix is symmetric and a real anti-Hermitian matrix is antisymmetric. They are the natural generalizations of symmetric and antisymmetric matrices to the complex domain. A real unitary matrix is an orthogonal matrix. Hence, it is the natural generalizations of an orthogonal matrix to the complex domain. A normal matrix is one that commutes with its Hermitian conjugate. A normal matrix is always diagonalizable by a unitary matrix. We next take up the eigenvalues of unitary, Hermitian and anti-Hermitian matrices. First, the eigenvalues of a Hermitian matrix and thus of a real symmetric matrix are always real. Second, the eigenvalues of a skew Hermitian matrix and thus of a real skew symmetric matrix are pure imaginary. Third, the eigenvalues of a unitary matrix and thus of a real orthogonal matrix have absolute value 1. Let us prove them one by one. Considering the first part of this theorem, let lambda be an eigenvalue and x is the corresponding eigenvector of A. So the characteristic equation will be A times x is equal to lambda x. Multiplying this equation by x star from the left so that x star into Ax is equal to lambda times x star into x. Now x star into x is equal to a row matrix with the elements x1 bar, x2 bar and so on till xn bar into the column matrix x1, x2 and so on till xn. This equals x1 bar into x1 plus x2 bar into x2 plus so on till xn bar into xn and is greater than 0. This implies lambda is equal to x star into Ax divided by x star into x. Now, x star times Ax is a scalar and therefore taking transpose has no effect. But A is Hermitian, hence A transpose is equal to conjugate of A, which implies is equal to complex conjugate of A. This implies x star into Ax is equal to the transpose of x star Ax, which equals x transpose into A transpose into X star transpose. This can be written as X transpose into A transpose into X bar, or it just can be simplified to give X transpose into A bar into X bar, which is equal to the X star into A into X on the whole bar. Hence, X star AX is also real, and so is lambda. So the first part of the theorem is proved. In the second part, consider that A is anti-Hermitian, then A transpose will be equal to minus of A bar. Following the steps of case 1 above, we now get lambda is equal to X star into AX divided by X star into X. So X star into AX is equal to minus of complex conjugate of X star into AX. The numerator is negative of its complex conjugate, and hence lambda is purely imaginary. So the theorem is proved. Third part now, let A be unitary and lambda be an eigenvalue, and X is the corresponding eigenvector of matrix A. That is, matrix A into matrix X is equal to lambda times X. The Hermitian conjugate of this equation is AX star is equal to lambda bar into X star. Multiplying the left-hand sides and right-hand sides of the two equations by AX and lambda X respectively, we have AX star into AX is equal to lambda bar into X star into lambda X. So this equals square of modulus of lambda into X star into X. But this implies AX star into AX is equal to X star into A star into AX, which equals X star into A inverse into AX, or X star into X, which implies square of modulus of lambda to be equal to 1. Hence, the eigenvalues are in general complex with unit modulus. So the theorem is proved. Let us discuss the eigenvectors of a Hermitian matrix. If A is Hermitian, its eigenvectors corresponding to distinct eigenvalues are orthogonal. Let us prove it. V1 and V2 be two eigenvectors of A corresponding to two distinct eigenvalues lambda 1 and lambda 2. Then A times V1 is equal to lambda 1 into V1. A times V2 is equal to lambda 2 into V2. This implies AV1 star into V2 is equal to V1 star into A star into V2, which is equal to V1 star into A into V2 and is equal to lambda 2 into V1 star into V2. So, lambda 2 minus lambda 1 into V1 star V2 is equal to 0, which implies V1 star V2 is equal to 0 since lambda 1 and lambda 2 are distinct. Hence, the theorem is being proved. Let us discuss the invariance of inner product. There is a one-to-one correspondence between the properties of orthogonal matrices in R raised to power n and unitary matrices in C raised to power n. First, the inner product in C raised to power n is preserved under a unitary transformation. Let matrix A be unitary matrix, then U is equal to matrix A into eigenvectors X and matrix V is equal to A into Y. Then, inner product of U with V is equal to U star into V, which equals X star into A star into AY. This can be written as X star into A inverse into A into Y. Since A star A inverse is identity matrix, so this becomes equal to X star into Y, or the inner product X with Y. Second point is that a complex square matrix is unitary if and only if its column vectors and also its row vectors form an orthonormal set. That is, if Ci and Cj are two column vectors of the unitary matrix A, then Ci, Cj equals Ci star Cj equals delta Ij. The proof is exactly the same as for orthogonal matrices. Only real space is replaced by the complex space. Third, let A be a unitary matrix, then determinant of A equals 1. The proof is again identical to the one for orthogonal measures. Remember that in this case, the determinant may be a complex number. So students, let us now summarize what we have learned in this module. We introduced the concept of eigenvalue of a matrix and discussed its importance in various fields of learning. Since the eigenvalue of even a real matrix can be complex, we introduced the complex vector space as a prelude to study of eigenvalue problem. Next, we introduced the characteristic equation of a matrix and obtain its relation to eigenvalues and eigenvectors of the matrix. Next, we define the very important class of matrices, the symmetric, antisymmetric, and orthogonal matrices. Then, we introduce orthogonal transformations and describe properties of orthogonal transformations in matrices. We define similar matrices and discuss their importance in diagonalization of a matrix. Finally, we define unitary, Hermitian, and Antihermitian matrices and prove various properties of their eigenvalues and eigenvectors. Thank you, students, for your attention.